In this video, we're going to learn about torque. Applying a non-zero net torque to an object causes it to rotate. So this is very similar to Newton's laws, where applying a non-zero net force caused a change in linear motion. Now we're talking about a non-zero net torque causing a change in rotational motion. Now force was just force on its own. We first have to learn how to calculate torque before we can apply sort of the equivalent of Newton's second law for torque. So we need to learn one half of the equation, and in another video I'll introduce the other half of the equation. So here we're going to learn that torque, represented by the Greek letter tau, is going to equal r times F perpendicular, where r in this formula is referred to as the lever arm. And the lever arm is the distance from the rotation point to where the force is applied. And I'm specifying very clearly here that this is the force perpendicular. So only the component of the force perpendicular to the lever arm causes a torque. So we're used to summing forces, but what's different with torque is the distance from the rotation point. So now we're going to find out that not only matters what force is applied, but where on the object it's applied. So before, when we were doing forces, we did free body diagrams where we reduced the object essentially down to a dot and just drew the direction the forces were going in. Now it matters not only what direction that force is applied, but where on the object. So we can no longer just reduce our object to a dot. We actually have to draw out the extended object and deal with the location where that force is applied. So what I've drawn down here is this is meant to be a door where you're looking straight down on the top of the door. So the hinge is here, this is the top of the door, and then like a door handle would be sticking out here. And I like to use a door because it's something we actually apply a torque to in everyday life in order to rotate the door open. So say here we have force 1 and we have force 2. And let's say force 1 is equal to force 2, so these are the same values. Which torque is going to be larger? So since the forces are the same, what's going to make a difference is where on the object it's applied. So this would be R1, and this would be R2. So R1 is less than R2, so that would make torque 1 less than torque 2, assuming, as I said before, force 1 and force 2 are equal to each other. So where on the object you apply a force changes the value of that torque. And this is why door handles tend to be near the non-hinge side of the door rather than close to the hinge. So if you've ever come across one of those doors where the door handle is actually just a flat bar across because it's opposed to twisting can hurt people with arthritis, that flat bar just allows you to push out. The only problem is you sometimes have to guess where the hinge is. And if you guess wrong, you can be pushing on the door and it won't open. If you push then on the other end of the door, it does open. So there is a reason why door handles are put in the location that is furthest from the hinge. Because furthest from the hinge allows you to maximize the amount of torque based upon how much force you're applying. Now I did specify that only the component of the force that is perpendicular to the lever arm is going to cause a torque. So remember, along here would be our lever arm. So if I apply a force like this, where you're given some angle in here, only the component that goes like this, which is 90 degrees from the lever arm, would actually cause a torque, which in this setup would be the y component. So we need force perpendicular. So only that y component in this case would cause a torque. And if we applied a torque or force like this, no torque would occur. So the torque would equal 0 here due to that particular force because the force is parallel to the lever arm. So that's why you don't try to open doors by pushing on like that lock insert because that is not going to cause the door to move because you're not applying a force in a direction that causes a torque. Torques can be positive and negative. So all the torques that I've drawn, or all the forces I've drawn so far, will lead to positive torques. So we define positive torque is one that causes the object to rotate in the counterclockwise direction. So if this is our rotation point here, this force is pushing up like this, which is going to cause the object to rotate around in a counterclockwise direction. So that would be a positive torque. On the other hand, a negative torque occurs when the force causes clockwise rotation. So if I applied a force in this direction, it would cause the object, remember the rotation point is still here, to rotate this way or clockwise. So that would be negative torque. And this goes along with the saying righty-tighty, lefty-loosey. So if you turn the object to the right, that is clockwise. So that would be negative, and that's whenever you insert a screw. So it would be going into the page or into the wall, which would be a negative z direction. On the other hand, if you do lefty-loosey, so turning it to the left, which is counterclockwise, the screw would come out of the wall, which would be the positive z direction. So that's where that saying comes from, righty-tighty, lefty-loosey, is it follows the same torque sign rules that we've established in this course. Now I've just indicated that coming out of the page is positive z and into the page is negative z. And so the torque causes motion in either the z direction, either positive z or negative z. So in essence what we have here is we have two vectors that are in a plane together because the force and the lever arm are perpendicular to each other. That is causing a third vector that points 90 degrees from that plane, because in my scenario I've been discussing, the force and the torque, or the force and the lever arm are in the xy plane, and your torque is applied in the z direction. So this describes the same thing as doing a cross product. So you can actually calculate your torque by doing R cross F. So if you're given the components of the force and the lever arm, you can do a cross product and establish what the torque is that way. Now remember, the variables must be done in the order they're written whenever you're doing a cross product. You can't flip them like you can for multiplication. So R cross F is not the same as F cross R. So make sure if you're doing a cross product that you do the cross product in the correct direction. And on one final note, torque does have units because everything in physics has units. And the units that we use for torque are newtons times meters. And I know a newton times meter is the same thing as a joule. But remember, energy and torque are not remotely the same thing, because whenever we did a force times a displacement in order to get a change in energy or work, which had units of joules, the force and displacement had to be parallel to each other. Now we're taking a force that's perpendicular to a distance from a rotation point and causing something to rotate. So they are not remotely the same quantities, even though it looks like they have similar units.